an important part of this course, as with any other courses, you got to develop an appreciation for what's good, right? And for what a good OS is. So what makes an OS good? Well, for one, it should be bug-free, right? And that kind of goes without saying. And it should work so well that you don't necessarily see that it exists. It just does its job. It's like plumbing. It should be robust. That means it shouldn't crash. And it should be of low overhead. So when it's not doing anything, like when it's idling, it shouldn't just keep drawing power or drawing a lot of power. And you should be fair in the sense that if you have several things that you want to be running on there, you should give all the processes a chance to do something without waiting too long. Should be secure by offering protection, and should be, well, helpful. That's kind of subjective, but then it's really to provide the right kind of service or right kind of primitive, right kind of operation. Okay, and OSs usually get the first blame when they don't work right. Okay, so this, the rest of this lecture, I'm gonna go over some historical perspective, and you can find some of the material in Chapter 1, but we'll do Chapter 1 next week as well. So we'll start with mainframes and then see how it evolves from batch system to multi-programming to time-shared, and look at computer systems architectures and their trends, as well as some special purpose systems. Then I'll go over the administrative issues. So mainframes, you may have heard of this term. This was from a long time ago, even before I was born. The computers, a lot of those were actually hand soldered or hand wired because they didn't have these integrated components. They were working with even these transistors or vacuum tubes, and they built a lot of those by hand, and they were huge. And the devices were slow, and you may have card readers, printers, but most likely text printer, tape drives. And they evolved, and you still get big computers today, but they are much more powerful, much more capable. So in the earlier days, how do you write a program or how do you input data? You use punch cards. It's like, what? Punch cards? So these are cards, and then you type on a keyboard, which then punch holes. And why? Because this is machine readable. So you can take a stack of these cards, feed it to a machine, and based on the holes that are punched, it can read the characters, and then that's what it takes to have program or data loaded into a computer's memory. And of course, if you happen to drop the stack of cards out of order, oops, you have to take time to sort them back. Or if you rip one, you have to type another one. And they rely a lot on human operators to do the sorting. So there could be maybe one person's data, or it could be a dozen programmers all wanting to run their program, so they each one hand a stack of punch cards, and the human then decides, okay, now I'll run your program, loads the stack, runs, and then prints output here. Next stack, right? It runs one job at a time, and of course, that's where the operating systems operating comes from. It's a human operator that loads and removes the stack, right? But if you have say, hey, my assignment is due, I gotta turn it in. Could you please put mine in front of the other guys? So you might bribe them, hey, here's a cake, and could you please order my stack before the others? Those things happen. But the point here is this is called batch system, because the person loads one stack of cards representing a program at a time. It runs until it's completed, then loads the next one. So, and then it's not interactive, right? When it's running, well, first you don't know when you get to run your program. Second, when they print it out, you might be sleeping, and then they call you, and then you go pick up. So it's called batch system. certainly this is not fun to work with, right? So then time sharing comes in, and that's possible only after you have more powerful processors and more memory, right? So instead of loading just one at a time run to completion, you load maybe several at a time, and then so they might be switching. Why? Because your program might actually be reading disk or writing or to tape, and those can be a long time, and the processor is not doing anything in that time. Well, guess what? That's when the processor gets to run another person's stack of programs, right? You can switch, and that's better utilization. You can overlap I/O with computation, so that's a good idea, right? And then that way, I mean, otherwise, if your processor is not fully utilized because it's spending all its time reading, writing tape, and processors not doing much, right? But multitasking on the timeshare system helps. But then you get into issues of limited memory, so that's what virtual memory comes in, and different people all wanting to touch memory, so you have the address space partitioning or memory protection. So I don't accidentally write to your programmed memory and corrupt your data, right? That's where protection starts to become an issue. Of course, storage, file system, and there you also want to be able to assign access permission. So if I write you a file, I don't overwrite your file, I don't read your data, right? And synchronization, that's when you have multiple things running concurrently. They may have problems, or even with deadlock, and it's stuck. Okay, so with these batch systems, you can do several jobs or repeated jobs fast without user interaction, and then it's allowing you to share system for multiple users at the same time, and you can or you can even schedule them. So perhaps you can say, mine is less urgent, so schedule me later or lower priority. But it's still doing one job at a time, and no interaction between user and then CPU idle. So overlapping I/O and computation is important for keeping these things utilized. And so the concept of spooling is developed. And that allows you to basically write your job to a disk, free up CPU to do processing, and CPU needs to be notified when I/O is done. Okay. And multiprogramming allows you to run several jobs, load several jobs into memory. CPU is multiplex, can switch. I/O may be spooled or interactive. And this interactivity is what enables the use of terminals. Right? A terminal, as you know, is a screen with a keyboard tied to a mainframe like this. And so when you type a keystroke, the processor switches to, with an interrupt or other mechanism, switches to your running job quickly and then switches back. Right? If that's all you're doing. And so it gives you that illusion that you can service many simultaneous users for bigger or smaller things. And it's switching so fast that you don't know that it's not doing these in parallel. It's emulating parallelism with concurrency. Okay, of course, you have the issue of memory management, CPU scheduling, I/O system. Now, multitasking system, on the other hand, is one that allows the CPU switching among jobs quickly, support interaction. User can see results immediately. So, right, so that's like you hit a key, you do the display, or mouse, drawing window. Right, so it might not be just doing your program. It might be doing several at the same time. Some in the background you don't see, but it does a context switch among multiple users. And so from batch to multi-programming to time shared, batch is single user, single job. multiprogramming would be to do multiple programs with better resource utilization. Now, time shared would be multiple user, multiple programs all at the same time. It allows interactivity and responsiveness. Okay, so batch systems, as you can see, is simplest. Very few OS features because a human is that OS. Okay? And multiprogramming, you do the CPU scheduling, memory management, I/O system, and for time share, you do need even more, potentially more synchronization support, virtual memory support, more protection, and faster context switching. Okay, and now, so for computer architectures, well, OSs were developed at the time when they only had single processors. And that's what traditional computers have been for a long time until the last couple of decades when you start seeing much more commonplace multiprocessors. And single processors, well, first they had limited technology, they could only build single processors. And later it was more cost consideration. But then when the technology became more mature, they could put multiple chips on there. It was really more of a power reason because if you can't just keep cranking up the processor speed and get performance improvement, and because power is going to grow quadratically. And whereas if you put multiple of them, you can run several things at the same time, but not so fast, right? And together you deliver the more throughput, more performance. So it was that consideration, and that's what, and also mobile computers, mobile devices emphasize power consumption as well. So really multiprocessors came about for several reasons. Now, but personal computers also went through a similar thing. Initially it was single user, single program, so DOS was like that. But then when you start doing like graphical user interface, initially, yeah, it was also one job at a time, but then you want to be able to say, hey, well, this is the transferring file, let me do word processor, right? You can see overlapping window, right? So it has more switching between multiple programs, but then initially they had to do it voluntarily. One program has to say, okay, I can give up my time, yield to another program to run, but if they don't yield, then it's stuck in one program, right? And then that's why you need what's called preemption. So that means even if you don't yield, the hardware takes control back from this program, gives it to this other program, let it run. And that's what you'll be working on for your project as well. You get to do little OS that will first do cooperative multi-threading, and then we'll change it to preemptive multi-threading. And by doing this, you'll get a much better understanding. But then, of course, the earlier systems didn't do much protection. So if one program crashes, it crashes the entire system. That's what your system will do too. But protection, that's really the only way to do it is with hardware support. So hardware has to support multiple modes of operation and also address space protection. That all requires hardware. Anyway, so earlier Windows were attacked a lot, viruses everywhere. Every other day you get an email from some user who didn't know their computer got hacked, and so it was a mess. But recently it got a lot better. And so modern OSs can do multitasking with protection. So I mean, even in the days of OS2, IBM did with Microsoft. They did. NT was Microsoft's collaboration with Digital, and that had multitasking and protection. So XP took a lot of the NT features. And certainly the Mac, when they switched to Next Step and then Mac OS 10 and so on, that was all Unix-based, so that had multitasking with protection. Now Android had a Linux core, and Linux was a Unix clone, certainly offers protection, multitasking. But back to processor architectures. So SPARC was Sun's hardware instruction set architecture based on Berkeley RISC, had the register windows. MIPS was Stanford's RISC architecture, and it worked its way into like a bunch of routers, game consoles. Alpha for a while was a champion in processor. It was running so much faster than all the other processors, but it was also sucking up a lot of power. And digital, that was really one of the last great things it did, and then it got acquired by Hewlett Packard, and then now just kind of disappeared. PowerPC was the alliance between Apple, IBM, Motorola, and IBM still develops power architecture. Apple switched to Intel architecture just because they weren't getting the kind of improvement that Intel was getting from collaborating with IBM and Motorola. Motorola for a while had some of the best processors, at least on the lower end, but they kind of just didn't continue with that. 68000 was used in the original Mac. It had it was 32-bit register but 24-bit address space, and then 030, 040. Those were pretty high performance for their day and very nicely designed. Of course, nowadays you see more ARM in your smartphone. A lot of embedded systems all go to ARM now, and they have embedded versions that are called Thumb 2. And higher, and so there's 3 classes of ARM. So for lower performance, server grade, and something in between. And then recently, Berkeley pushing RISC-V architecture as an open source. Why? Because ARM really was British root, and because as you know, U.S. likes to control everything, so they say we gotta get that control back. Okay, RISC-V there. So that's the U.S. attempt to get control back from ARM. Anyway, parallel systems got developed, and parallel there's actually different kinds. But the word parallel actually does mean something more specific. It's not just multiprocessor. It actually means tightly coupled multiprocessor system. And there's also, as you can imagine, loosely coupled. Tightly coupled means they are not far apart. They're together, most likely on the same board or very close together. Whereas loosely coupled can be all over the place, here and then maybe one over there, and they communicate over a much slower link. So tightly coupled means they communicate over high speed, very high speed bus. And in fact, they even share memory, whereas loosely coupled, you can probably share memory. Or if they share memory, that's going to be very inefficient. Okay, so parallel system, this is certainly one of the first things people think of. Now I have processors, they're cheap. Let me put 10 of them, see how they work. Well, do you get 10 times speed up? Not necessarily, right? Because first, is there that much parallelism? And second, there's always places where you can't parallelize, right? But still, people build these for several reasons. And even parallel systems are divided into what's called SMP, so symmetric multiprocessors versus asymmetric multiprocessors. So symmetric ones, as you can imagine, right, they all run same OS, and that's still most popular, and you can have them do, like a lot of the Intel ones, the i3, i5, i7, these are symmetric. Asymmetric means you have different kinds and play different roles. One would be master, the other would be slave, and master tells slave what to do. Right? And this is more common in these very large systems. And multi-core is what you have a lot in general purpose today, especially mobile ones. And I mentioned one reason, power was one reason. They couldn't afford to clock these faster. I mean, even 1 gigahertz is kind of that sweet spot. Go to 2, 3, even 4 gigahertz, it's going to be really hot, and you run out of power. And even if you don't run out of power, you burn your lap, right? It's very inefficient. And so it's better to clock them slower, but then on this, have several of them. And now they can put quite a few CPU cores on the same chip, and that's what you get with these Intel Core architectures, right? And and also they can do very fast on-chip communication compared to off-chip. So now in terms of energy efficiency, yeah, it's much better compared to a single processor clocked at a much faster rate. And you also have these what's called many cores. How many is many? Well, it could be up to several thousand. So like these GPUs, you may have heard of, right? General purpose graphic processing units. They were initially used for accelerating graphics operations like ray tracing, the layering, all that. But then they became used for general purpose, and now a lot of them used for machine learning as well, which is also very high demand for computation. And they are not your general purpose like your CPU cores. Instead, you program not individually but a bunch at a time. And they have separate address calculation, and they schedule the memory access to avoid contention. And they can achieve very high performance, so almost like supercomputer performance. So NVIDIA certainly is one of the most well-known ones. Intel also has their many core, maybe not as many as these GPU ones, but still the Xeon class, more server class, and they can have a lot of performance using not as many cores, but because each core is much more powerful compared to like the GPU. And there's tile mesh architecture, right? So there's these many core processors. And now, so when you have multiple processors, whether tightly coupled, loosely coupled, or many core, how do you organize the memory, right? So they can share the same memory, or they can have their own memory, or they can have a bunch share memory, but then you have a bunch of bunches. And so you can have, right? So, but every time you try to share memory, that becomes complicated because you would need multiple read-write ports. And what happens if they try to access the same location? You have some conflict, right? And so if you do share memory, you are limited by the architecture capability, right? And memory design, you can't have too many ways of sharing memory. I mean, 4 is by a high number. If you try to do 20 processors sharing memory, no, that's not going to work very well. And so then what you have is then this hierarchy, right? So several of them share memory, but then if you want to talk to some other ones, well, they talk over some other bus. Yeah, yes, you can get to some other group's memory, but then that'll take much longer time. So this is called non-uniform memory architecture, or NUMA. Okay. So IBM Blade server is known for being a good NUMA architecture. And you have distributed systems, so these are loosely coupled, right? So because you can do tightly coupling only up to a certain limit. I mean, how tightly coupled can you be, right? You're limited by the laws of physics, the speed of light, and also energy density. You're gonna have to also have cooling problems. Server rooms usually require a lot of cooling. And now loosely coupled ones are much more scalable. So data centers, or Google, Amazon, right? These big servers, they run loosely coupled or distributed systems. Why? Because then they are serving different requests that can be processed more or less independently, right? I mean, there's some dependency, but you can solve some with duplication. So this is what enables really the very, very large scale. But it's really for the amount of parallel workload rather than just pure performance. And so this allows you to do resource sharing, load sharing, reliability, and they can be organized either peer-to-peer or client-server. Right? So client-server is where you have more like the website, right? You want to connect to Google or Amazon or these Facebook, right? So they have a server farm running, and you don't know or don't care where it's running, as long as it gives you back what you are requesting. But then server can become bottleneck, so they do all kinds of tricks at the network level to redirect traffic. But otherwise, if all you have is a single server, then that could be a single point of failure. But that's mostly solved. And server usually has a bunch of these machines on this network to redirect its traffic. Peer-to-peer is more like you have these machines with the same role, and any one of them can be as good as any other one as far as the user is concerned. So you may have seen these like BitTorrent, PPStream, and so where when you connect to one, I mean, as long as it delivers a service, you don't really care which one, right? So this can have potentially better scalability. And then, of course, there's clustered systems. Now, clusters are used a lot in these storage or shared storage, your cloud drives, and so forth. And so they basically you can make your own cluster if you want using conventional PCs, but you connect them in these racks. So could be a rack would be like a couple dozen machines, and then have racks that connect, and they connect over a high speed like a fiber optic or InfiniBand, MirrorNet. And so one example that's pretty popular is people use Beowulf. And you can have what's called asymmetric and symmetric clusters. Now, asymmetric is one where one server runs application, others are standing by, whereas symmetric ones means you can have two or more hosts running applications and monitor each other. Okay, so system architecture developed over time from tightly coupled, from single core to multi-core to multiprocessor, and then that's kind of the limit of your more tightly coupled. Then to scale any larger, you have to go to loosely coupled. So you have cluster, distributed, and so forth. All right. All right. So those have been the general purpose systems. Now let's take a quick look at these special purpose ones. So real-time systems you may have heard of. They may be used in several places, like your airplane, your anti-lock brakes, your factory automation, all sorts of things. What makes them special is they need to be able to meet timing constraints. Now, timing constraints may come in the form of deadline. Could be what they call minimum separation, maximum separation, and it could be aperiodic or periodic. Okay, and whatever it is, it doesn't have to be fast to be real time. Although being fast kind of helps, because being slow means there's certain tight timing constraint you might not be able to meet. But just being real time doesn't mean it's fast. Okay. What's important is it has the ability to guarantee that it can meet the timing constraints. So multimedia system, industrial control, flight control, autopilot, anti-lock brakes. Depending on the kind of application, they may have different scales of timing constraints. A lot of them tend to be a few dozen times a second. So multimedia system, you're talking about frame rates. So every frame may be a deadline, and these frames could be 30, 60, 120, up to 200 some frames a second. And audios have frames too. A lot of mechanical control, even airplanes or cars, they also have frames about 20 to 50 times a second. Okay, and these anti-lock brakes may need faster or shorter constraints. Now, real-time systems are also divided into what's called soft real-time versus hard real-time. Hard real-time ones tend to have severe consequences if you don't meet the constraint. So, like a nuclear power plant, if you don't control the valve properly, then nuclear meltdown. That's bad, right? So it has to be a hard real-time constraint. It has to really guarantee. When I say deadline, I mean deadline. Whereas other things are less harmful. So like you're doing streaming video, watching YouTube, and then oops, drops a frame. Most likely nothing bad happens. You just get annoyed, right? But if you're in the Tesla autopilot, you fall asleep. It misses some deadline. Oops, you crash into a big car, right? So hard real time, soft real time. Anyway, now so real time systems don't have to have an OS. Reason for mentioning this is, do you really need an OS? Well, it depends. So, a lot of real-time systems are built without OS, but most research on real-time systems use some or rely on some OS or scheduler. You don't have to have an OS because you can do scheduling all in advance or offline scheduling. And in fact, Boeing, the maker of a lot of these passenger airplanes, For a long time, they had to hand schedule their code in assembly language. And they don't trust OS. And then once it works, they're using processor from several decades ago. Why? Because it works. No sense changing it. They're very conservative, at least for a while. Now they try to use newer things, but they are very, very conservative. And some people simply don't trust OSs, especially for some of these real-time systems, hard real-time ones. Anyway, multimedia systems, right? Audio, video, these are pretty well known, and in fact, you often work with some communication protocols, so that even if you miss frames, the encoding allows you to recover or get a lower resolution version. So if you've ever done some streaming, sometimes high resolution, and then for a while, if you see blurry picture for a while, or right, and then so depending on the traffic. Well, that's really with the encoder working, because they spread out their traffic so they can vary your bandwidth kind of on a best effort basis. And if you drop packets, they can reconstruct the data from other frames that they actually receive. So they're pretty robust that way. So it's better than nothing, right? So these are soft real-time, and they rely on their algorithms and coding protocols to allow to tolerate misses, so because they can't really always control, and they can't enforce hard real-time constraints. They just use it, leverage that as a feature. Mobile and embedded systems, of course, the term changes a lot. We build embedded systems in my lab, and there is these embedded processors on small circuit boards. Now, PDAs, for ones who were considered embedded systems. Now your touch panel for air conditioning control, that could be considered embedded systems, but it may run an OS behind. Could be Android, could be something. Smartwatches often have, pretty much all have OSs there. Health fitness bands, smart homes. There, I think it's more several considerations. One is feature, one is cost. So for those who don't care about the cost, yeah, you can put all the fancy features as long as people buy it. But a lot of times they are cost sensitive because you sell a lot of these, and so making use of resources, whether it's the cost of the processor, cost of the battery replacement, how much power consumption, packaging, weight, right? These are all limiting factors. So the role of OS in different computer systems, well, it comes back to runtime support. You don't necessarily just design the system for once. You want to be able to evolve over time. You want the code to be maintainable, to add features, fix bugs over time. Having a structure, a stable structure, is nice, because that means if you have to replace your hardware, change to a different processor, add a new feature, you wouldn't have to rewrite your code, which you would have to do if you had to touch the hardware directly. So that abstraction is nice. Stable structure is nice, right? And so depending on what you're doing this for, feature consideration, compatibility considerations. Okay, so that was a quick overview of different computer systems, how they developed over time, and OS's role in them, or lack of roles in them. Okay, so starting from these mainframes, batch processing, multiprogramming, time sharing, right, that progression. Batch is when you load one at a time, and multiprogramming allows you to load several, and then but still it's doing one at a time. Time sharing allows you the system to force context switch. Tightly coupled evolved into loosely coupled, and of course the memory architecture has to become more non-uniform over time, right? Because you can only share up to a certain scale, and beyond which you have to rely on more distributed structure. And distributed structure is really the current limit of the global scalability. And real time is the hard real time versus soft real time. Okay, I'm gonna spend the rest of the time talking about administrative issues. That's me and my email and my office, this building, 6th floor. We have 5 TAs for this course, and they are all here in this corner. So I guess you may have met them before, but please stand up and wave your hands. So they're your best bet to doing well in this course. If you have questions, please ask them and be nice to them. Okay, now you may sit down. And course website. So yes, there is a course website, and so all the announcements will be made through this course website. Okay, so you need to be proactive, and I mean sometimes we send out notification email as part of updating a page, but not all pages allow us to do that. You should make it a habit to check this course website. And there is also a discussion noteboard. Let's see, maybe let's go to there. Oh, wrong page, here, there. So, okay, this is my view. I wonder if I can switch to student view. Oh, somebody added this, okay. So yeah, oh yeah, by the way, yeah, we post materials, including lecture slides, supplemental materials, data sheets, even recorded lectures. Oh, I try my best recording all the lectures. It's really not to encourage you to be absent. It's in case you really can't make it, at least you have a way to view it. Or if you have trouble keeping up with English, this is a chance for you. Because I'd rather have this than having like 20 tape recorders in front of me. So anyway, so yeah, we will post lecture recordings. It may take us a little bit of time to do some processing and compression. Okay, so the lecture materials, but you do need a Google account, the NTHU G Suite for Education account, or GAP account. And this is the website that tells you how you can apply for one, okay? And you have to authenticate using your GAP. You may have a personal Gmail account, and if you try to access and logged in as your personal one, it says permission denied, and there's a switch account or request permission. Please don't click the request permission. Please switch account to your, otherwise I get emails requesting permission when you already have the permission. Okay, so just switch account to your GAP account, and then you can access. Why do we do this? Because these book publishers give us slides to use. Hey, use our slides. What I do, and then they say, oh no, you use our pictures, and that's copyright. Oh, okay, fine. So and and the only way we can do this is we lock it behind or make it access limited to students on campus. I don't think there are any spies from publishers, so they can't really see what we're doing on campus. So anyway, so if you're logged in with your GAP account, you should have access to the materials. Okay, that's the way that publishers find acceptable, so we'll respect that. And there's a bunch of things you can do. Discussion forum on here, and a bunch of things. Okay? I don't use all the features, like I don't use a separate calendar. You just look at this one.